Hello, everyone. This is the first new material of the semester. So we're starting with section 6.1, the area between curves. So it's going to help a lot to remember the intuitive idea of the integral, that if we have a function f of x, then we can think of the integral as the area below the curve to the x-axis. Okay. So we are going to talk about the idea of area between curves today. Okay, so what if we want to find this green shaded region between the curves f of x and g of x? All right, well, it wouldn't just be the integral of f, right? Because the integral of f would include this area here, it'd go all the way down to the x-axis. And then the integral of g of x would only be this white shaded area. So how can we find the green area? Okay. Why would we bother doing this? Well, just like with integration, where it has many possible uses, there's many possible uses for this. So for example, if f of x represents sales of a company and g of x represents expenses, then the area between the two curves might represent profit or net revenue. All right, so a lot of applications, but how do we actually find the area? So, or the area between these two curves. The idea is pretty straightforward. We have our curve f, and we have our curve g. As I said before, if I just did the integral of f, I would have this entire blue region here, right? And if I did the integral of g, I would have just that green region. And I want to get just this yellow region. So how can I find that? Well, I'm going to start with the blue region, the integral of f, and I'm going to subtract away the integral of g, that green region. All right. And if I do that, I'll be left with just that yellow region. So the area of the area between the curves should be the integral from a to b. Okay, so I'm in all of these cases, I was integrating from a to b. So the area between the curves should be the integral from a to b of f of x minus g of x. Right? F of x would give me that blue area. G of x would give me the green area. So if I subtract away g of x, I should get that yellow area I wanted. So this is the most simple case. We're going to make things a bit more complicated as we go. Usually, we're not going to be given the bounds. So maybe in these cases, we are told, okay, find the area between the curves between the points A and B. Okay, so maybe we won't always be given those points. So we'll talk about how to deal with that situation. Just a note that it doesn't matter if one of these functions is positive, one of them is negative, as long as we have one function that's clearly on top or above the other, we can deal with all these situations. But order does matter. Okay, so these are the cases we can deal with. Okay, so maybe f is positive and g is negative. Okay, the integral f minus g is still going to give me this blue area here, that area between curves. And same thing with this. It doesn't matter if g starts positive and then goes negative, or if everything's positive, like in this case. This f minus g is always going to give me the area between the two curves. But order is important in that I always want the top curve to be in front. Okay, so I always want my integral to be f minus g. If I do g minus f, it's going to give me a negative number, which I don't want. All right. So when these problems are asking for the area between the curve, we want a positive number that is just the clear, intuitive area between two curves. We're not talking about signed area. We're just talking about the real world idea of area. So that should be positive. So if we get a negative number, we know we've done something wrong. Okay. So again, the formula for this area between curves should be, we have our bounds, the integral a to b. Okay, we're going to be given those in this most simple case. And then we're, let's see, integrating the top function, whatever that is, minus the bottom function. That's always going to give us the positive number that's associated with area between curves. And again, if we did bottom minus top, we would get a negative number, which we don't want. So let's do a quick example. Let's find the area of the region bounded by these curves. Now, these are important curves, and these are technically curves, but they're really just our bounds, right? What's x equals 0? That's just this vertical line here, our y-axis, right? So the important part is that it's giving me a bound right here. That's going to be my a. And then what's x equals 2? It's this vertical line here. So I'm going to stop integrating at 2. So that 0 is going to be my a, and 2 is going to be my b. Okay. Now, how I always start these problems is I draw the curves to get an idea of what's going on. So I draw my curve y equals 4x, this steep vertical line or diagonal line. And then I draw my parabola y equals x squared. And I see this green shaded region is enclosed by these curves. All right, so that's the area I'm looking for. So I need to set up my integral. So which function's on top and which one's on bottom? Well, clearly the y equals 4x is the top function, right? And y equals x squared is the bottom function. Okay, so that's what I've said here. And then, as I said a moment ago, our bounds are going to be the x equals 0, x equals 2. So usually in these problems, they don't say explicitly, okay, a is equal to 0, b is equal to 2. They'll give you this sort of situation where they give you these vertical lines. Okay, so those are usually going to be the bounds in this most simple case. So I know I can set my integral as the integral from 0 to 2, 4x minus x squared. Okay, I put everything in parentheses. So I put the top curve in parentheses and I put the bottom curve in parentheses. So really what's important is this, okay? And I do this because a common mistake is people don't distribute the negative when they subtract f minus g, okay? So for example, if I had the integral x squared minus x minus 2, I need to remember to distribute this negative here. So when I distribute that negative, comes this, all right? So I put everything in parentheses just to keep everything straight. And then this last set of parentheses is just a style thing. Okay, so my integral should be from 0 to 2, 4x minus x squared. I simplify everything, okay? And then I integrate using my power rule, okay? And I should get 4 over 2x squared minus x cubed over 3 from 2 to 0. Excuse me. And when I evaluate that integral, I should, after simplification, get 16 over 3. So this problem is just setting up the integral, and then the rest is just the integration that we should already be fairly comfortable with. All right, so as I said, things are going to get a bit harder as we progress. So let's just talk about the next level of difficulty. Perhaps we are not given these bounds. Maybe they don't tell us what the bounds are in any format. They don't give us any clues. So the questions that look like this are usually phrased, find the area enclosed by the curves f and g. So this kind of key word here is enclose. So So here's an example of a problem we might see in this style. So let's say the problem is phrased, find the area enclosed by y equals x squared minus 2 and y equals negative x squared plus 16. So this, when they say find the area enclosed, this means that we're going to end up with, we're going to draw our curves and we should see a single region that is enclosed by the curves, meaning trapped or bounded by both curves. And that's going to be our region, and we have to figure out the bounds of integration ourselves. So if I draw y equals x squared minus 2, okay, well, that's going to be this upward facing parabola. And if I do y equals negative x squared plus 16, that's going to be this downward facing parabola. So if I draw these, I see this region in the middle that I've colored yellow that's enclosed by these curves, okay? So looking at this region, well, let's see. If I was going to try and apply my previous method, I would need to figure out which curve is the top curve, which curve is the bottom curve, right? So what's the top curve? Well, it looks like it's this here, which is y equals negative x squared plus 16. And then the bottom curve would be this, the bottom parabola. Okay, that's y equals x squared minus 2. But what are my bounds of integration? I want to integrate from the leftmost point where I have some area to the rightmost point. Well, the leftmost point is, let's see, this blue dot, right, where the curves intersect. And I want that x value, so I need to figure out what this x value is. I'm going to call that my a. And then I want to integrate until the curves intersect again, and we'll call that b. Okay, so that's the setup for this. And now I've just restated some information here. The top curve is y equals negative x squared plus 16. Bottom curve is y equals x squared minus 2. So the integral should be, and I've put everything in parentheses again to keep my negative straight, negative x squared plus 16 minus x squared minus 2. And after I distribute my negatives and simplify everything, my integral should be this negative 2x squared plus 18. If you're wondering where that came from, start at this step and go ahead and simplify, and you should end up with the same thing here. Then we're asking, all right, where should we integrate from into? Well, we discussed that already. That's what we want to integrate from the leftmost point where the area exists, the rightmost point. So that leftmost point is going to be where the curves intersect, and the same thing for the rightmost point. So how do we find where these curves intersect? Well, I'm going to set these curves equal to each other. And then I'm going to solve for x, essentially. Now, there's a technique here that I want you guys to use that'll make things a bit easier in the long run. And we'll see an example of why this is important at the very end. But trust me on it for now. The best way to solve for these intersection points is to move everything to one side of the equal sign. So I want to move all my x's and constants over to the same side, and then I should have 0 equals 0 on one side, 0 equals some function. Okay, so let's go ahead and move everything to one side. I move everything to the right side. On the left side, I'm just left with 0. On the right side, I have 2x squared minus 18. Well, if 0 equals 2x squared minus 18, I'm just going to make things a little bit easier for myself. I could divide both sides by 0, right? On the left side, 0 over 2. Well, 0 over 2 is still just 0. Okay. So I have 0 equals x squared minus 9. Okay. Now, from here to here, what I've done is I've just factored in my head here, but you can use any factoring method you want or use the quadratic equation to find these values, okay? And you end up with positive and negative 3. So this A, this point we talked about earlier, that's my negative 3, and B is my positive 3. Okay. A little, before we move on, a little note about graphing. Okay, so I graphed these parabolas, and maybe I intuitively had a good idea in my head of what this would look like. But when I was drawing these curves, if I'm just doing a rough sketch, you know, I had my intersection points up here, which that should be accurate. But maybe if we are just doing a rough sketch, I draw my parabolas, and just from the way I've sketched them, I get my intersection points, you know, kind of funky. So remember, when you're drawing these curves, that this is it depends on how much work you put in. If you put a lot of painstaking work on the graphing step, then okay, maybe your intersection points are accurate. But if you just do a quick sketch to get an idea of what's going on, keep in mind that what you've drawn might not be 100% accurate. But then when we get to this step of solving for our intersection points, that should give us a clearer idea of what's going on, okay? So for example, let's say I take the point x equals negative 3, and I plug it into this bottom curve here. When I plug that in, I should get, let's see, y is equal to positive 7, right? So I know that this intersection point is actually going to be at negative 3, positive 7. So yeah, this picture of where it is, that does make some sense, okay? If it was down, if I had drawn my point, my intersection point down here, and I saw I was at the coordinates negative 3, positive 7, well, I would know that would make a lot of sense. Regardless, I've found my bounds of integration. They should be those intersection points from negative 3 to positive 3. And then I've already found the function I'm integrating. It's negative 2x squared plus 18. So now the rest is just integrating that. Okay? And we should end up with 72. Feel free to try these intermediate steps on your own. When some steps are old material or stuff you should be familiar with, I'll oftentimes kind of skip over the simplification. Great thing about YouTube is you can just pause the video and work along and see if you agree with me. So just some notes on this process. So some notes on this process of finding the region enclosed. The area should be unambiguous and finite, okay? So we're not dealing with infinite regions. And it should be clear from the statement of the curves what region we're referring to. So there's a common mistake people make, that they naturally stop drawing at the x-axis or y-axis, but don't do that unless you're explicitly told to do so. So I'll kind of show you what I mean by an example. Let's say we're told to find the region enclosed by these three curves: y equals 2x, y equals 1/2 x, y equals negative x plus 5. Let's figure out what this region is. It should be this blue shaded region. Okay, so how did I do this? How did I figure this out? Well, first thing to do, let's kind of start from scratch here. This will be a rougher drawing. First thing to do is draw all the curves you're given, okay? So let's see, I draw my y equals 2x. Let's say that's this curve here. And then let's see, another one of the curves was y equals 1/2 x. So let's go ahead and draw that and say that's there. And then we say, okay, well, we had the third curve, negative x plus 5. Okay, so that looks something like this. So there's a lot of triangles here, right? Well, is it this? Is it this? Is it this guy? Which region is it? Well, there's only one finite region enclosed by these three curves. Okay, you might think it's this region here, this little triangle, but you might naturally be using this y-axis as a bound, right? But in the statement of our problem, it never said to stop at the y-axis. So if I tried to choose this region, that region would actually, it would be, sure, it'd be here, but nobody told us to stop at the y-axis, so it would just keep on going, okay? So not a finite region. And then same thing for this region here. You might naturally be using the x-axis as a bound, but nobody's told us to stop at the x-axis. So that region, again, wouldn't go down forever. It would include this stuff and then go down forever. Okay. So there's only one finite region enclosed by these three curves, and that would be this region in the middle. Okay. So on this side, it's enclosed by this curve y equals negative x plus 5. On this side, it's enclosed by y equals 2x. And then here, it's enclosed by y equals 1/2 x. Okay. So there's only one correct choice for this shaded region. Okay. So here we've seen area enclosed by three curves, which brings us to our next level of difficulty for these problems. It's areas enclosed by more than two curves. So maybe we want to find the area enclosed. We don't want to just find the shaded region. We want to find the area of that shaded region. So how do we do that? Can we have two curves subtracted from one curve? You know, our previous setup was f minus g. How do we deal with more than two curves? How do we deal with three curves and so on? It's a similar setup, very similar setup as the previous case. We're just going to have to chop our region into pieces, basically. So let's use the same curves as previous. We want to find the area of the region enclosed by these curves, y equals 2x, y equals 1/2 x, and y equals negative x plus 5. So let's just redraw our region here. And let's try and figure out our top curve, okay? So I asked this question, which is the top curve and which is the bottom? Well, that really depends on where on the graph we're looking, right? If I'm looking at this inside this left triangle here, okay, well, right now the y equals 2x is on top and the y equals 1/2 x is on bottom, right? But if I come over here to this right piece, that situation changes, right? Now this negative x plus 5 is on top and y equals 1/2 x is on bottom. Okay, so what I'm going to do is I'm going to split my region right down the middle. Okay, where this this change occurs, and where does that change occur? It occurs where these two curves pass through each other. Okay, so I'm going to split my region down the middle, and then I'm just going to use my normal method to find the area of this region, and then I'm going to separately find the area of this region, and then I'm going to add them together to get my total area. Okay. So this is just a restatement of what I've said. The left piece, the top curve is y equals 2x, bottom is y equals 1/2 x, and so on. So I'm going to chop my integral up into pieces, right? So this integral, I don't know what the bounds are yet, but this should give me the area of my left piece. and this integral should give me the area of my right piece. Now, let's figure out the bounds for each piece, okay? So going back up to the picture, what are the bounds for this left region? Well, just like in the previous problems, let's see, I'm not given the bounds, I gotta find them. So what's this leftmost point? It's where this curve y equals 2x intersects this curve y equals 1/2 x. So I'm gonna set those curves equal to each other and solve for x. Okay, so that's what we're doing here. I've set 1/2 x equal to 2x, and I'm solving for x. And again, I like to get everything to one side of the equation and all my variables and constants to one side. And I just want to be left with 0 on the other side of the equation. Okay, if you had just divided by x, you would have gotten 1/2 equals 2, right? And that just doesn't make sense. So it makes a bit more sense if we move everything over to the right side and we get 0 equals 3/2 x. Well, when is that true? That's only true when x equals 0. Okay, and then we need to solve for our right endpoint of this integral. Okay, what is that? Where are we going to stop integrating this first piece? I want to integrate from here, and then I've chopped my area up into two pieces, and I've stopped integrating. Well, I switch integrals at this point, right? So I want to stop integrating at whatever this point is. What is this point? Well, the x value is the same as the x value up here. So what's the x value up there? Well, that's where these curves y equals negative x plus 5 and y equals 1/2 x intersect. So let's solve for that x. I set 2x equal to negative x plus 5 and solve for x, and I get x equals 5/3. Okay, so my left integral should then be the integral that's going to give me the area of the left region should be 0 to 5/3, blah, blah, blah. What about the integral for the right piece? Well, where's it going to start? It's going to start at this same x value, right? 5/3. And then it's going to go to whatever point this is, okay? So we're saying, okay, it's starting at that same x equals 5/3. And then we need to find that other endpoint, b. That's going to be the point where the line negative x plus 5 equals or intersects the line 1/2 x. So I set those two curves equal to each other and solve for x to get x equals 10/3. So now I can set up my complete expression. I got the integral that's representing the area of my left piece and the integral that's representing the area of my right piece. So my first integral is going from 0 to 5/3. The second integral is going from 5/3 to 10/3. And then I just solve these integrals. And again, I'll trust you guys to check me on this to make sure all my math is right, my arithmetic. But we should get an integral like this, and I didn't even bother simplifying the number values. Okay, so I'll let you guys plug that in for yourselves to see what the actual area is. Okay, we have one final level of difficulty. In the previous cases, it was clear, even if we didn't know the endpoints, we could draw a picture of our curves and we could see, okay, this curve's on top and this curve's on bottom. And that's important, right? Because we want to subtract top minus bottom, right? We never want to do bottom minus top. So it's important to know which curve's on top and which curve's on bottom, but that might change in the middle of the problem. So what if we have curves like this? What if I'm told to find the area enclosed by the curves f and g? Okay, well, let's see. Over here, oops. Over here in this left piece, this curve's on top. Well, which curve is this? That's going to be the curve f. right? Let's see. So we're on top here, the curve's down, okay. Yeah, so F is on top for this piece. And then what's on bottom? Green's on bottom for this piece. Or excuse me, G is on bottom. What about for this piece of the graph? Well, it switches, right? Well, now G's on top and F is on bottom. And I've actually stated this backwards. One moment while I correct that. There we go. All right, so if I divide this region up into sections, let's call this this is the section. Let's call this the left section, where it exists between the points. Let's call them A and B, where these curves intersect, right? Okay. So from A to B, F is on top and G is on bottom. And then let's say this right region is from B to C. Okay. From B to C, G is on top, F is on bottom. So the total area would be the integral from A to B, f of x minus g of x, plus the integral from b to c of g of x minus f of x. So I want to make sure in each integral I have top minus bottom. Okay, that's what I have in this left piece. And then at the point B, the curves switch, they swap positions. So I still have top minus bottom, but these two expressions are different. I have f minus g on this left side, g minus f on this right side. So just make sure that you're always integrating top minus bottom, and you might have to break your region up into pieces to ensure that. So as a last example, let's find the area enclosed by the curves y equals x and y equals x cubed. Okay, so if I draw my region, I again see, all right, this is a situation where I have curves swapping positions. In this left, piece here, y equals x cubed is on top, okay? And on, let's see, then y equals x is on bottom. Okay? So that's what I've stated here. And then in the right piece, it's the opposite. Y equals x is on top, y equals x cubed is on bottom. So I need to set up my integral like this. I got my left piece and I got my right piece. Okay, so what are my bounds? And this is what I alluded to earlier. I want to show you guys why moving everything to one side of the equal sign is important, especially when we're dealing with polynomials, right? So to find, there's 3 points I need to find, right? I need to find this point here, and this point here. Well, this middle point is clear, it's 0, right? But maybe our graph this is a fairly simple example. Maybe that point would be slightly harder to find. Okay, so where are my bounds? What are these 3 points of my integrals? Okay, to find those, I need to find all the points where my curves x and x cubed intersect. So I'm going to start by setting x equals to x cubed, and then I'm going to solve for x. Okay. So at this point, I'll kind of introduce the common mistake people make. We've set x equals to x cubed, and then the temptation is to just divide out x from both sides, and you get 1 equals x squared. Okay. Well, that's true, and then that would give us the values, what? -1 and +1. But what about the 0? Okay, this doesn't include the point x equals 0, right? So how do we figure out where that point is? Okay, it's that's why this method of moving everything over to the right side or left side, doesn't matter, moving everything to one side of the equation is a bit better. So we get 0 equals x cubed minus x. And then this is a polynomial that I can factor. And if I factor it correctly, it's going to give me all roots. It's not going to leave out this x equals 0. So I factor this expression on the right side. And it factors like this, right? And now I can see that my roots are going to be x equals 0 coming from here, x equals +1, x equals -1. So that's an example of why this method is a bit better for finding these points of intersection. Okay, if we use this kind of naive method, we might leave something out. Okay, so again, back to finding our bounds. We set x equal to x cubed. We move everything over to one side of the equation, and we factor that polynomial to get the roots 0, +1, -1. Okay, so going back up to this picture, let's see, I can fill those in. Okay, well, this should be at the point -1, that should be at the point 0, and that should be at the point +1. So my left integral should be from -1 to 0, and my right integral should be from 0 to +1. And then the rest is just solving these integrals and plugging in values, and we should get the value 1/2. So that covers all the examples from this section. I will do a problem video with more examples of me solving these problems. I'll try and do a couple from each level of difficulty. Let me know if you have any questions.